Hello dear students. Today we are going to introduce to sets and numbers, the first chapter in our book. What do we mean when we say set? Although mathematicians invented the notion of set around the middle of the 19th century, we encounter sets in our everyday life, at work, at the market, in the streets, even in our brains. We may even say that set is an order in chaos. The most distinguishing property of a set is that there is a certainty in its construction. When a set is given, its elements should be understood in the same way by everyone. For example, some trees, a group of students, or a bunch of dogs does not form a set. It's not clear what kind of trees, which group of students, or what breed of dogs we are talking about. In mathematics, a set is a collection of well-defined objects. Many problems that may be solved through the use of sets easily may not be solved simply easily, or may not even be solved at all. So sets are a tools in solving problems. Mathematics loves saving. So how do we denote sets? We have three ways of denoting sets. The first one is the listing of its elements. Consider the first 5 letters of the English alphabet. Now, if we put commas in between these letters and put these letters inside the curly braces, we use this notation, the listing of the elements of the sets and of the set E. So this is the listing of the elements. Another method is the Venn diagram. If the Venn diagram is named after the English mathematician John Venn. In this notation, we place all the elements of the set in a closed area encircled by an ellipse. The third notation is the implicit representation, or the closed representation. In this notation, we just use a rule to represent all the elements, a common rule to represent all the elements of a set. For example, to denote all the letters in the English alphabet, we just use the letter X to denote a letter in the English alphabet. Now think that if you had written all the letters in the English alphabet, you would have used 26 letters. So this is the shortest notation in denoting the sets. Let us now consider the shops in a certain shopping center. Let us denote this shopping center by M. Denote the set of shops on the first floor by F, on the second floor by S, and on the third floor by T. Now, since the set of shops on the third floor is already in the shopping center, T is a subset of M. Now, let's assume that there are 13 shops on the third floor, 10 of which are clothing shops and 3 of which are shoe shops. Since the clothing shops are on the third floor, C is a subset of T, and since the shoe shops are also on the third floor, S is also a subset of T. We denote this by C is a subset of T. Also, these shops, the clothing shops and the shoe shops, are already in the shopping center, so they are also subsets of the shopping center M. Now, let's say we are trying to find clothing shops on the first floor, and we realize that there are no shops on the first floor. So, the set of shops on the first floor is an empty set. Also, we are looking for bookstores on the first floor. We realize that there are no bookstores on the first floor. So, it's also an empty set. How many empty sets do we have? Actually, 1. We denote all empty sets by the same symbol, which is given by a vertical line on 0. Now we try to define some operations on the sets. Just like adding and subtracting numbers, we can define some certain operations on the sets. The first operation we are going to define is the intersection of sets. Let us be given 2 sets, A and B. The set of all elements that belong to both the sets A and B is denoted by A intersection B, and it is the elements that belong to both of the sets. Now, for the union of sets, once again we are given 2 sets A and B, and we define the union of these 2 sets as the set which contains all the elements that belong either to A or to B. This is denoted by A union B. If two sets A and B have no common elements at all, we say that these sets are disjoint sets. So the intersection of these disjoint sets is empty. Another new operation that we may define for sets is the difference of sets. Two sets are given A and B, and if we remove all the elements of B which are already in A, we obtain a new set which we call A minus B and denote it by A backslash B. We may similarly obtain a new set by removing all the elements of A from the set B, so that we have B minus A. And we denote it by, again, B backslash A. Now, in the difference of sets, the order of difference is important. So either we are subtracting B from A or A from B is very important, as we will see on an example shortly. Now we have another new set, which is the complement of a set. And in order to define this notion, we need a new concept called the universal set. Suppose that we are talking about the first year students in a school. So first year students in a school is a subset of all the students, or the set of all the students in the school. So we may regard the set of all students in a school as the universal set. Or we are talking about some old dogs, and we are talking about some certain breed of dogs. So this means that the set of all dogs is the universal set for a certain breed of dogs. In this way, we may define a complement of a set as the elements which are not in A is the complement of the set A in this universal set. Now, let us try to give an example of these notions and how we use them. Consider the set T, which is the set of all letters in the Turkish alphabet, and consider the letters of the English alphabet. Consider the set of letters of the English alphabet and denote this set by E. Now, since A is a Turkish letter, it's in the alphabet, we say that A is in T. Since Q is not a Turkish letter, we say that Q is not in T. Now, from these two sets, we construct two new subsets. The vowels in the Turkish alphabet are denoted like this. And the vowels are already in the Turkish alphabet, so the set of vowels in the Turkish alphabet is a subset of T. We can also construct the vowels in the English alphabet and denote it by VE, and VE is a subset of the set E, which is the letters in the English alphabet. Let us now combine these sets in the way of unions, intersections, and so on and so forth. Now, the intersection of the vowels in the Turkish and English alphabet is given by A, E, I, O, and U. So this is actually the letters in the set of English vowels. We can also combine these sets by the union operation. If you combine these sets by the union operation, we get the whole vowels in the Turkish alphabet. And from these two sets, we can construct the different sets. If we subtract the vowels of the English alphabet from the Turkish alphabet, we get this set, which is I, Ö, and Ü. If we subtract from the vowels of the English alphabet the Turkish vowels, we get the empty set because they are all common, and if we remove all the Turkish vowels from the English vowels, we have nothing left. So as you can see, as we mentioned before, the order of difference is very important. Now we move on to the subject of numbers. How many? In order to answer this question, people developed many counting methods throughout the history. Numbers are the most frequently encountered objects in our everyday life. In our shoppings, in our recipes, in the weather forecasts, in student grades, even when you are calculating the interest rate on some investment you put on a bank, we use numbers. So, to able to count, humans introduced the the numbers what we call today the counting numbers. The numbers 1, 2, 3, and so on and so forth are called the natural numbers. 0 is not a natural number, on contrary what some sources say. This is because 0 means non-existence, and we count by existing objects. That's because it took hundreds and hundreds of years to introduce this 0 into the mathematics literature. Humans developed new number systems according to their needs. For example, we use the same number to 100 to talk about our debt or a payment we are to receive. If we assume the sea level to be 0, how correct is it to denote a submarine below the sea level, 100 meters below the sea level, or a bird flying 100 meters above the sea level? Here, the negative numbers is introduced. Thanks to negative numbers, we denote our depth by minus 100. We denote the submarine below the sea level, 100 meters below the sea level, by minus 100. If we add the negatives of natural numbers along with 0 to the natural number set, we obtain a new set, which is the set of integers. Since all natural numbers is in this set, natural numbers is a subset of the integers. We can also show the set of integers on the number line. To do that, we place 0 on the number line and then equal space the negative and positive integers, so that we construct this notation. Still, we encounter in our daily life that integers is not enough. For example, when we are talking about half a glass of water or 1/6 of a piece of cake, integers does not help. We denote these quantities by natural numbers, so the rational numbers. So rational numbers are the ratios of integers. Since all integers can be written as z equals z over 1, integers are already a subset of rational numbers. We can also place all rational numbers along the real line by properly scaling the real line. So if you want to put half on the real line, we just divide the unit length 0 to 1 by half and just put the 1 over 2 on the line. How about, do we have any more numbers than rational numbers? Let's see. Let's think about a unit square, the sides of which are equal to 1. Let's connect the corners of this unit square and construct the diagonal. And let's try to calculate the distance, calculate the length of this diagonal. From the Pythagorean theorem, we see that this length is given by the number root of 2. Root of 2 is not a rational number. It's proved about 2,300 years ago, but the proof is out of the scope of our book, so we are not going to present it here. Numbers like root of 2, root of 3, root of 5, which cannot be expressed as the ratios of integers, are called irrational numbers. So the relation between all the number sets we have so far introduced is like this. Natural numbers is a subset of integers, which is a subset of rational numbers, and the union of rational numbers and irrational numbers is the set of all real numbers we know of, which is called the real numbers. We may now talk about the powers of numbers. The powers are a useful notation to denote very large and very small numbers. For example, the product of 4 5s, 5 times 5 times 5 times 5, can be denoted by this notation 5 to the 4, which saves a lot of time in writing and a lot of space. For an arbitrary n, we may denote a to the n and mean that we are multiplying the number a by itself n times. In this notation, a is the base and n is the exponent. The powers are especially useful in denoting very large numbers, as we said. For example, consider the distance of the Earth to the Sun. It's approximately 49,600,000,000 meters, which is very difficult to write and which is very long to write. Instead of this, we use the power notation, exponential notation, to show it as 1.496 times 10 to the 11 meters, which saves a lot of space. What do you think is the diameter of an atom? How large is an atom? It's approximately 0.1 nanometers, which is, when you write it explicitly, 0,00, a lot of zeros and 1. It's difficult to count all these zeros. It is denoted by 1 times 10 to the minus 10 meters, which is a much shorter notation and it's much prettier. So I tried to introduce the sets and numbers in this lecture, and hopefully you are going to learn a lot from your book. And I suggest you solve all the questions in your book. There are very nice examples and exercises. See you in our next lecture.